Okay, let's dive deep. We're cracking open some source material today, and the big theme is how we make computer programs faster.
Yeah, how we get that speed.
And often that speed comes from a really clever balancing act, a trade-off.
Absolutely. In the world of algorithms, raw speed, well, it usually isn't free.
Yeah.
You gain something in one area, speed maybe, but you might have to give up a little something else.
And the most classic trade-off you'll see, I think, is between time and space.
Mm-hmm.
That means trading execution time for memory usage, or, well, the other way around. As our sources explore, sometimes use less memory but take longer.
Right, or sometimes you use more memory, maybe quite a bit more, to finish much, much quicker.
So our mission in this deep dive is to really get our heads around one incredibly powerful technique that kind of perfectly shows that second trade-off, using more space, more memory to gain a massive amount of time. Speed, basically.
And we'll use a common, really foundational problem as our guide. It's a perfect illustration.
And that problem is this. Imagine you're given a list of numbers, right? And a specific target number.
Okay.
Your task is to find any two numbers within that list that add up exactly to that target. And, crucially, tell us where those two numbers are located in the list, their original positions, their indices.
It sounds simple on the surface, doesn't it? Just
Yeah.
find two numbers that sum up. Easy.
Seems easy.
But the difference in how you search for those numbers, especially, that list gets bigger and bigger.
Yeah.
That's absolutely fundamental to building efficient programs. This problem, the two-sum problem, it's like a cornerstone for understanding algorithmic efficiency. Getting it right helps solidify concepts you'll just use everywhere. It's worth spending time on to really remember.
Okay, so let's start with maybe the most intuitive way, the brute force way you might first think about tackling this two-sum problem like our sources describe.
Right, brute force. And it is what it sounds like. You just tried every single possible pair of numbers in that list.
Every single one.
Every pair. You check. Do they add up to your target? No real subtlety, just, exhaustive checking.
And the way you'd actually write the code for that, the material says, is usually using nested loops.
Exactly. Nested loops are the classic way. You'd have one loop, the outer one, to pick your first number. Let's say it's at index I.
Okay.
Then inside that, you start another loop, maybe from the next position, I plus 1, to pick your second number, say at index j.
Ah, so you don't pair a number with itself or check the same pair twice in reverse?
Right. And inside that inner loop, you just check. Does numsci plus numsjj equal the target?
You're basically setting up this system where the first number gets checked against every other number after it, then the second number against every number after that, and so on.
Precisely. You keep going until you either find a match or you, well, run out of pairs to check.
Okay, so you're checking potentially a lot of pairs. What does that look like efficiency-wise? How long does this brute force thing take as the list gets bigger?
Right, let's talk time complexity. We often use big O notation for this. So if your list has n number, n items, yeah, the outer loop runs, well, n times, roughly. The inner loop, for each step of the outer loop, it also runs roughly n times, or maybe closer to n2 on average, but in big O terms.
It's still proportional to n.
Still proportional to n. So the total number of checks is roughly proportional to n multiplied by n.
Which gives us
Or n squared. Okay, let's make that concrete. If the list has 10 items, maybe around 100 checks, give or take. If it has 100 items,
then you're looking at something closer to 10,000 checks.
wow, and 1,000 items.
Million checks, roughly.
Million, okay.
That quadratic growth, the squared part, is incredibly significant. Doubling the size of your input doesn't just double the work, it quadruples it.
Oof.
Tripling the input makes it maybe 9 times slower. This is where brute force methods just hit a wall really, really quickly as your data scales up. Yikes. Okay, that sounds painfully slow for, well, anything but the smallest lists. What about the other side of the coin? Memory usage. Space complexity.
Well, that's the good news for brute force, as the sources point out. Its space complexity is O1.
O1, meaning constant.
Exactly. Constant space. You really only need a few variables, one to track the outer loop index, one for the inner loop index, maybe store the target sum. It uses a tiny constant amount of extra memory, and crucially, that amount doesn't change whether your list has 10 items or 10 million.
Okay, so connecting back to our big idea, that trade-off, the brute force method is a super clear example of trading time for space, right?
Cool.
It's incredibly memory efficient, O in space, you can't beat that, but you pay a heavy, heavy price in how long it takes that O into time, especially for larger problems.
Precisely. Minimal memory footprint, but potentially a maximum time commitment as your inputs grow.
All right, so that O and 2 time is it's a killer for performance. How do we fundamentally break out of that quadratic trap? How do our sources suggest we make this search dramatically faster?
Okay, this is where it gets interesting and where that other side of the trade-off comes in. Trading space for time.
Using more memory to get speed.
Exactly. And the key tool here, as highlighted in the material, is using a specific data structure that's designed for extremely fast lookups. A hash table.
A hash table. Okay.
Sometimes you'll hear it called a dictionary or maybe a map, depending on, the programming language you're using. Python calls them dictionaries. Java often uses hash map.
Got it. So instead of just blindly checking every pair like before, we use some extra memory, this hash table, to get smarter about how we search.
That's the core idea.
Hmm?
And the really elegant part is that we only need to iterate through the list once. A single pass.
Only once, down from nested loops.
Just one pass.
Yeah.
And as we process each number in that pass, we're going to use the hash table to instantly answer a really crucial question.
Okay, walk us through that single pass. How does the hash table actually help?
Okay, so imagine we're looping through the list one number at a time, index by index, say left to right.
Yep.
For the number we're currently looking at, let's call it num_c at index I, we immediately figure out what the other number in the pair must be to reach the target sum.
Yeah, how do we do that?
Simple subtraction. It's just target num_c. Let's call this the complement. It's the number we need to find to make a pair with the current number.
Okay, makes sense. Like if the target is 15 and my current number is 7, the complement I need is 15 minus 7, which is 8.
Exactly. Now, here's the magic. Instead of starting another loop to search the rest of the list for that 8, we instantly check our hash table. We just ask it, hey, hash table, have I already seen the number 8 during my path through the list so far?
Why would the 8 be in the hash table? How did it get there?
Because of what we do if the complement isn't found. Here's the sequence for each number num_c.
Okay.
1, calculate the complement, target num_c. 2, check if that complement is already in the hash table.
Right. 3.
If it is in the hash table, we're done. We found the pair. Complement was seen earlier.
How do we know where it was?
Because when we add things to the hash table, we don't just add the number. We add the number as the key and its index as the value.
So the hash table stores number index pairs.
Precisely. So if we find the complement, say 8 in the table, we immediately get its index back. We have the index of the complement from the table, and we have the index I of the current number 7. Those are our two indices. We can return them right away.
Wow. Okay. So if I see 7 now, calculate I need 8, look in the hash table, and boom, 8 is there with its index. I've found my pair instantly.
Instantly. Within that single pass, you found the current number num_c and his partner, the complement found in the hash table. Return their indices. Job done.
That feels incredibly fast compared to checking potentially thousands of pairs in the brute force method. But, okay, what if the complement isn't in the hash table when I look? What happens then?
Good question. If the complement isn't there, it just means we haven't encountered the number needed to complete the pair with the current number yet. It might appear later in the list or maybe not at all.
So what do we do?
We prepare for the future. We take the current number, num_c, and its index, I, and we add that pair, num_c_i, into the hash table.
So we store the number we just saw so that if its complement shows up later in the list.
Exactly. If we later encounter a number whose complement is the num_c we just stored, the lookup will succeed and we'll find the pair.
So the hash table is constantly growing as we iterate, storing everything we've seen so far and its location, acting like this super fast index or memory.
You get it. It's like building a quick reference guide as you go. And this is where the massive speedup comes from. The fundamental operations on hash table, checking if an item, a key, is present, and adding a key value pair are typically incredibly fast.
How fast?
On average, they are O1 operations.
O1. Constant time again. Like the space complexity for brute force.
Yeah, constant time on average. That means, generally speaking, checking if a number is in the hash table or adding a number to it takes roughly the same, very small amount of time, regardless of whether the hash table already contains 10 items or 1,000,000 items.
Wait, really? It doesn't get slower as it gets bigger?
Not on average, assuming a reasonably good hash function and implementation. There are some technical details like hash collisions, which can, in worst-case scenarios, degrade performance a bit. But for most practical purposes and well-designed hash tables, you can think of lookups and insertions as taking constant time, O1.
Okay, that O1 lookup is the heart of the speedup then. Let's nail down the overall efficiency numbers for this hash table approach compared to the brute force one.
Okay, time complexity first. With the hash table method, we only do that single pass through the list. Let's say there are n numbers.
Yep, n items.
For each of those n numbers, what do? We do a calculation, subtraction, a hash table lookup, check if complement exists, and maybe, potentially, a hash table insertion. Add current number and index.
Okay, a few steps per number.
Right, a constant number of steps. And crucially, those hash table operations, the lookup and the potential insertion, are O1 on average.
So n items, and for each item, we do roughly O1 work.
Exactly. So the total time complexity is n times O1, which simplifies to just ON, linear time.
ON time. Wow. Okay, that is a massive jump down from ON too.
Ouch.
Let's go back to our 1,000-item list example. Brute force was maybe 1,000,000 operations, ON2. With this hash table method, ON is more like 1,000 operations.
Roughly, yeah. Maybe a few thousand, depending on the constant factors hidden in the O1. But the key is it scales linearly, not quadratically. If the list doubles to 2,000 items, the work roughly doubles to 2,000 operations, not quadruples to 4 million.
That's incredible. It fundamentally changes the game for larger data sets.
It really does. This is the power of using the right data structure for the job. That hash table unlocks linear time performance here.
Okay, amazing speed gain. But we know there's a trade-off. What did we trade for that ON speed? It must be memory, right?
Yes, absolutely. The cost is the hash table itself. We needed that extra storage.
How much extra storage? What's the space complexity?
Well, think about the worst-case scenario. Maybe the pair that sums to the target involves the very last element of the list.
Okay.
In that case, as we iterated through the list, we would have added almost every other number and its index into the hash table before we finally found the complement.
So the hash table could potentially grow to hold almost all n elements from the input list.
Exactly. Therefore, the space complexity for this hash table method is ON. The amount of extra memory needed grows linearly with the size of the input list.
Right. So let's recap the comparison. Brute force, slow, ON2 time, but super lean on memory, O1 space. Hash table method, lightning fast, ON time, but uses more memory, ON space.
That's the core trade-off for this problem. Laid bare, you've got the two sides. And the sources we looked at, they generally highlight that for this specific two-sum problem, the hash table approach is usually considered the optimal solution in practice.
Optimal. Why optimal if it uses more memory? Is it just because the speed up is so incredibly significant?
Precisely. That dramatic reduction in time complexity going from quadratic ON2 down to linear ON is almost always deemed worth the increase in memory usage from constant O1 up to linear ON.
Especially as the input size then grows larger.
Definitely. For small n, maybe the difference isn't huge, but as n gets into the thousands, millions or more, ON2 becomes completely impractical while ON remains feasible. Most real-world systems, they prioritize speed for the user experience, and having memory scale linearly with the input size is usually perfectly acceptable for typical data sizes on modern hardware.
This really makes that principle crystal clear. We essentially replaced a slow sequential search, that inner loop of the brute force method just grinding through the remaining elements.
Yeah, that linear scan within a loop.
We replaced that with a single, blazingly fast, hash-powered lookup, O1 average time lookup.
Absolutely. It's a perfect and I think very memorable example of how choosing a data structure specifically designed for rapid access, the hash table in this case, is often the key. It unlocks dramatic improvements in algorithm efficiency, provided you're willing to accept that corresponding, often linear, increase in memory usage. Understanding this pattern, this space for time exchange, is just fundamental. You see it again and again when trying to solve programming problems efficiently. It's a concept you really want to internalize so you can spot opportunities to use it.
So this deep dive into just this one problem, the two-sum problem, it really gives us a powerful, concrete example. Using a different data structure, like the hash table, fundamentally changes the performance. It makes that abstract idea of trading space for time really tangible, something you can really grasp and hopefully remember for a long time.
Yeah, we saw exactly how investing a bit more memory that scales linearly with the input, can unlock just immense speed gains, turning ON2 time complexity into ON. That's huge.
Okay, so final thought for everyone listening. Think about the problems you encounter, maybe not just coding challenges, but everyday things. Searching your email inbox, maybe. Looking up contacts on your phone. Even how websites load data quickly.
Yeah, or how databases find records.
Where might similar time-space trade-offs be happening behind the scenes, under the hood, to make things feel instantaneous? How much memory, invisible to you, is being used right now to give you that speed? And maybe, when you're building something yourself, how much memory are you willing to sacrifice for that kind of speed? It's a fascinating question.